format works like this. Doesn't matter what segment register you're talking about, they all follow the same format. And this is it. 16-bit, right, guys? So here's our 16-bit container. The bits 15 all the way down to 3. This forms the segment select. Okay? It's called the segment selector. This bit right here is the TI bit. Does anyone remember what that stands for? Or anyone know? Table indicator. Okay? This is the requested priority level. We're not going to worry about that. We're going to assume that everything is incredibly high priority. We're not going to even deal with it. Okay? So, you notice the table indicator. What do you think that does? If the table indicator is 0, it's what's referred to as a global access. Global. What does global mean? Go. Do not raise your hand. Speak up. Okay. Global variables, global data. Who is it available to? All applications, right? Anything running, whether it's Notepad or your banking app, right? And everything in between, right? What's that? There you go. If it's 1, local. What does local mean? That are actually being run at that time. Okay, so an access to a variable that's local to a method, that would be a local access, not table indicator bit specifies. Okay, and again, the compiler would set table indicator bit appropriate. If it's a system call, like for system timer date or something, well, it's going to be okay. Bottom line is there are two segment table. Now, the segment selector is a 13-bit value, right? Do the math, 13 bits. 13-bit value that specifies a segment descriptor. What do you think a segment descriptor is? Word apart. Shout it out. Describes it. I don't remember. Nathan. You nailed it, Nathan. It describes a segment. Now, if you're going to describe a segment, you can think of a segment as if the entire memory available to you for the entire everything, including hard drive, if we call that memory land, a segment would be a block of memory land. Okay? Back in the good old days, the bad old days, the good old days, segments were defined as 64K. That's the way Microsoft and not Microsoft, Intel, the hardware development. Now we have variable length segments. So do you see the descriptor has to specify what? How long it is, how big the block is, and the base address. Do you see that with those two pieces of information, the processor knows exactly where the block is in the entire Big memory. What, 2 terabytes, 3 terabytes, something like that. I forget what the entire address space is, including. Main memory is only 4 gig. Yeah, 2 sounds right. Remember. So the segment descriptor specifies the length and what's called the base address. A base address of something is simply the address of the beginning byte, nothing more. Okay. Now, the format of the segment descriptor looks like this. It's 8-bit or 8 byte, sorry. Oh, it is? Okay. I can erase, but why don't I just erase it, Nick? Is that readable? Okay. So, segment descriptor is 8 bytes long. Okay. How do we know that? Well, I just told you. But the segment selector is 13 bits, right? The least significant 3 bits are not part of the segment selector field. Okay. And we're going to use that to work to our advantage and you'll see how that works in a moment. So we need 2 things, right? Base address, right? And size. Well, the size is called the limit. Okay. It's the highest value that is called an offset register, and I'll show you how that highest value that the offset register can be and still be inside the. Okay. Do you see that bad things would happen if a memory access tried to access a byte of memory that wasn't inside the same segment that was being specified? That would be bad, right? Right? Segments exist, among other things, for protection. Okay, so if Nathan's code is running, I don't know, Nathan, what application are you like Chrome or something? Would that work? Okay. And Ryan's Excel, right? You look like a spring. Okay. It's a compliment. It's a compliment. It's a compliment. No, not a database. No. You see one database, see them all. Should accesses from Ryan Excel be able to access anything in Chrome, Nathan? They should be divorced, shouldn't they? Right? Bad things happen when references in Excel go into Chrome's memory space and vice versa. So we're gonna explore how all this stuff works, and these protections are actually enforced. Okay. This is the segment descriptor, right? Every single segment descriptor follows this format. 8 bytes. It's a recurring theme. 8 bytes. How long do you think the basic? How many bits would you need for the basic? I gave it away indirect. 8-bit. How big's memory land? Main memory. Main. That's virtual memory. That's virtual memory. Virtual memory equals main memory, cache, plus the disk. Okay. That's why it's called virtual memory, because you're the programmer, you think you have this 2 terabyte, like, I don't need to worry about memory. I have 2 terabytes. Well, yeah, most of them are on the hard drive, which is a really, really slow access media, especially compared to cache memory. So main memory has been for 30 years, has been 4 gig. That's the memory space. Whether or not it's all populated, I don't know. But processors support 4 gig. Okay. 4 gig, to access any byte within that 4 gigabyte main memory, you need 32 bits. 2 to the 32nd is 4 gig in chain. 4 billion. Okay. So it's 32-bit. Do you see that? Well, 32-bit is 4 bytes, right? Right? So the base address is specified by bits 31 through 24 are in what's called byte 7. This is byte 7, 5. Go. That's what. So this is the base address, most significant byte. The next byte is right here, and it's bytes 23 through 16. The next 2 bytes, this byte 4, byte 3, byte 2, they contain the least significant 16 bits. Okay. So this is I'm gonna erase this. Just please understand this is 2 bytes, not 1. It's bits 15 through 0. Does that make sense? So you concatenate those 4 bytes together, you get the base address. Pretty simple, right? The limit, that's the other thing we need, right? Because we have to know how big. We found out where it starts, base address, need to know how big. The limit is 20-bit, okay? And there's lots of reasons for that. Not going to get into them now. It's the least significant nibble of byte 6. So this is limit 19 through 16. The other 16 bits, that's 4, 20-bit limit. The rest of them are right here. Bytes 1 and 0. You concatenate those 20 bits together, you get the limit. Okay? Question for you. What's the maximum size of a segment in this scheme? Isn't it 2 to the 20th? You got a 20-bit limit. 2 to the 20th. How big's that? 1 meg. 1 meg. So the default maximum size is 1 megabyte. Guys, you can get a lot done in one. Okay. If you looked next running his laptop, I assume you're not doing anything crazy. Yeah, and you're obviously the OS is doing all sorts of things that you don't know about nor care, right? I would bet money that very few, if any, segments in your lap. Maybe close, maybe half a meg at most. You know, if you're running some graphic stuff, but for the most part, small segments are the way to go, and that's why we have this. So this limit field can be smaller, so we can have more segments and operate more efficiently. I hope it's obvious to you that large segments don't lend themselves well to efficiency. right? Because you can't pack as many in, and you would probably have some empty spots in memory. So um, that's why we have the script now. Segmentation. Wait. Now, what I sent Nick earlier today, and what you see here is a descriptor, segment descriptor. I created it. Does it actually exist? I don't know. In some computer in a galaxy far, far away, a long, long time ago, maybe it did. I don't know. It doesn't matter. For what we're doing now, I wanted to show you how the descriptors work, and then we can take that and show you how segmentation works, and then on to, you guys ready to roll? I beg your pardon? What? Oh, I think if I remember right, this is access. And that again, that's who can access the segment. This is one of the methods that the operating system uses to keep Ryan from accessing stuff that Nathan is supposed to hold. Now, Ryan can give, or Nathan can give Ryan access by setting this bits in this. I never really studied how it works. I just know it does. Okay. These, I don't remember what these are. One is, no, I don't think so. I'd have to look at, one specify, no. I'll look at it tonight or sometime and get back to you. Okay, let's go through some examples, and I'm going to steer the examples because I know which memory accesses are going to work throughout the entire scheme in the handout I gave you. It was rigged. Yeah, it was rigged. So I'm going to clobber this, all right? Okay. So suppose the data segment register contains, 0x 0b b3. Extra segment contains 02E7. Okay. What segment descriptor do these segment registers point to? Well, we have the technology, we know the format, so we just got to run it through the format, figure out which descriptor, and then look in these tables and figure out what the heck the descriptor actually contains. So then we can get the base address and limit. Does that make sense? Everybody good? Okay. So the first thing we got to do is convert this to binary. Do you see that? Yes, no? So the data segment contains 0000, 1011, 1011, 0011. Base. Got it? Binary to hex. If you've had digital logic, you better have that nailed down. What's the table indicator bit? 0. What does that imply? It's a global. The descriptor is in the global descriptor table because the table indicator bit is 0. Which descriptor? Well, clobber these, right? So we're dealing with this. Now, what I do when I'm dealing with stuff like this, and I want to convert it to packs, which is what we're going to do. I put little carets where the divisions for the hex symbols would be, the hex digits. Shout it out, Noah. And yes, no? Where is that? Well, the base address for the descriptor equals the descriptor number. That's not hashtag. Okay, that's the number sign. Rebecca? It's not. It's the pound symbol. I wrote as a unit of torque. I wrote this in statics the other day, and my students, what's a foot hashtag? Foot pound, not foot. How do we know they weren't? Actually, they did. You're right. All those hieroglyphic things, right? Right. Well, all of our knowledge pretty much built upon stolen knowledge. No, it's not stolen. It's reused. Anyway, you multiply descriptor number times 8. How do we multiply anything times 8? Especially if it's in binary and or hacks. You just shift. Or it is. So what's the descriptor number? 0176, right? So 0176, this is hex. Convert it to binary. Going to do it the long way. Yes, no? Add 3 zeros to the end. Put your carets back in. Right? What do you end up with? 0, B, 0. So I ask you guys, gee, doesn't that bear a strange resemblance to the contents of the data segment register? Like it's the data segment register with the least significant 3 bits zeroed out? Do you really think the microprocessor, each and every single memory access, is going to go through this multiplication or shifting or what? Do you really think that? It's not. All they do is they take the most significant 13 bits out of here, okay, copy it to a register, to an internal register that has the least significant 3 bits as zeros. There you go. That's the base address of. Got it? Now, where are the descriptor tables? Where do they reside? You only got one spot, bits to reside. Memory land. Okay, all this stuff is in memory land. Okay, so we have the descriptor base address, but do you really think that that's the physical address of the? It's not. So what we do is this serves as an offset into global descriptor. Well, if it's an offset, that means that it's added to a base address, no? Right? What's the base address of the global descriptor table? Well, look at the top of the screen. The global descriptor table register, which has a format that I'm not going to bore you with, remember, but the most significant 2 bytes matter, the least significant 2 bytes do not when it comes to locating the global descriptor. So the global descriptor table register is what? That's the base address of the descriptor table, the global descriptor. That's the base. Add the offset to it. 0BB0, yes, no? What do you get? 08620BB0. And again, do you really think the processor is going to go through the trouble of adding? No. It takes the global descriptor table register and just plops this value into the least significant 2 byte. That's all it does. Where in the table do we see this address? 08620BB0. Oh, it is? Oh, crud. Really? It probably, yeah, you're probably right, Justin. Did I fix it? Okay, but I got to shift it up so we can get all 8 bytes, right? Yeah. It's so yes, no? What's the base address? Oh, by the way, we need to move over. I can do it. I got it. I got it. Wrong way. Wrong way. Is that coming through? How's that? Up, up. We good? Who's with us? Donut. How you doing, Brennan?
Good. How are you doing?
Okay. Having fun. Lots of fun.
It looks like it.
Yeah. Oh, yeah. Definitely. Yes, now? Where'd I get that number that I just wrote? Yes, no? What's the limit? Oh, but timeout. Okay, which table? Here's one table contents. Here's the other table content. Which one's global? Which one's local? You can deduce it. Where do you get that, Nathan? There you go. Right here, right? Well, that matches the global descriptor table register value. This is global. This is local on this side. Okay. What are you laughing at? She won't. I know she won't. What's the limit? Least significant nibble. So we have a pretty darn small segment. That's okay. That's all right. Good things come in small packages. Um, what about the other one? No comment. What about the other one? What about the other access? I'll do it over here. What's the extra segment contents? 02E7, right? Okay. How do we find the base address of the descriptor? Because we really don't care descriptor number, do we? Processor really doesn't care. It cares about the base address. How do we find it? Is what? What do? We just zero out the least significant 3 bits of the segment register, right? So zeroing out 7, right? Just set all those to zeros. Okay. Shout it out. Which descriptor table? Local or global? Okay. What's the LDTR contents? Do we care about the least significant 2 bytes in the LDTR? No, we add the offset to it. What do we add? This value right here, right, guys? Oh, we need, I always do that too, Nick. Where's this in the table, lady and gentlemen? Oh, it's definitely on the right. Oh, is it? Is that right? This guy? Got me worried there for a minute. What's the base address? What's the limit? Limit's the same thing. When I was doing this earlier today, not creating this, not editing it, I was really super duper tempted to pick another descriptor that didn't have the same limit. That would have jacked the other 4 pages up. So sorry, guys. Limit's the same. Okay. Now, um, suppose this is from your handout, guys. Number 3 in the handout. I give you some instructions and the contents of BX. Okay. Okay. Um, 2 instructions. We got to move DX, comma, ds colon bx. The brackets mean use bx as an address, not a value. Okay. The second instruction is a move ECX ES colon BX. So a similar instruction, right? Similar, different segment content. Okay. Well, we already know what DS contains. We already know what descriptor DS references, right? DS DS accesses 80F0. Where's that at? This one, right? This guy, right? Okay. So the base address is what we found right here. Yes, no? Well, that's the base address of the segment. BX is an offset register. Do you see that? What do you do with an offset? Add its contents to the base. Okay. So the address, the what's called it's called a linear. The linear address is 80F0F930 plus 4. Where do we get the 4 from? BX. BX, right? It's the offset, right? So we go to the beginning of the block, which is 80F0F930. We go to the beginning of the block, and we go to the fourth house in, right? Actually, the fifth house, offset 4, because it's okay. How many bytes are we? Where do you get 2? You're right. Whoever said that, either Justin or Noah. How many bytes do we have to move? DX is 16-bit, guys. Many of you don't know that DX is 16-bit. So it's going to move 2 bytes. Which 2 bytes? We're going to find that out in about 30 seconds. Okay. Well, we have to go to the linear address memory map. Yes, we have a linear address memory land and we have a physical address memory land. They are not the same. Okay. I wonder which memory land would be this. No, you don't live in memory land. You're not so blessed. Yeah. What does it go for? What's the address? Well, the segment pointed to by ES, isn't it this one? Isn't it space address here? Right? Everyone give me an amen. Come on. Right? So the base address is 80. Help me out, guys. 30. Is that correct? Plus what? Plus what? 4. It's the same PX register. So this goes to 8030003C. Okay? What's at those locations? Before we move to that, are there any questions whatsoever, guys? Talk to me. Move? It's in the handout. Yeah, it's in the stuff I. Are you good? Is everyone else good? All right. So now, can we move on to the next page? Talk to me. So we can move on to the next page, and I got to erase all this stuff 'cause it's not going to be pertinent anymore. This is our pretend linear memory land. It is. I keep thinking that the physical address memory space, that should be the RIDS, right? You know, the linear address space is that in the middle class, right? The logical address space, well, that's just the slurs. The logical, yeah, they live inside your. What generates the logical address, guys? Your code. Okay. So, um, uh, guys, help me out. What were the descriptor numbers? 176, G176, is that right? Help me out. Right here, yes, no? Right? The segment, this is the global 176 descriptor with 176. We don't have, we already calculated the base address, found it. What was the other descriptor number? Did we even find it? I don't think. What's the base address of the other segment? Uh, what was the base address of the actual segment, though? Was it 80300038? That was the base address of the other segment, right? Well, we barely have enough room. No, I did not plan this. And the limit was 7, right? This is local 5C. We didn't break this up, figure out the descriptor number. Okay, we just went right to the base address. Okay, but it's descriptor 5C, which starts at the segment it describes is okay. So for the move, I'm going to repeat the move instructions, guys. DX comma, what was it? DS:BX. Oh, do you guys understand how this table works? Each entry is 4 byte. Okay. This is the least significant byte. So this the 52 here would be the byte at this address. B5, the byte at B5 would be 90 hex. The byte at B6 would be 32 hex. The byte at B7 would be 98 hex. Okay. That was my notation. Okay. Do we talk about little endian format in computer architecture? We do, don't we? Yeah. This is little endian format, right? Least significant byte first. Okay. But that's why, guys, that's why the addresses increment by 4 as we go from one row to the next. That's why they increment by 4. Okay, does that make sense? If I did 1 byte per cell, it'd be. I'm sorry. Which one? This. Yeah, go on, Noah. Yep. And I knew how big the segment was because they're both limit 7. I made it all nice and neat. Okay. What was the base address for this one? Wasn't it 80F0F930? Right? So we're going to move 80F0F93, not 0, but 4, correct? Because BX equals 4. What's that? We don't want this house. We don't want any of these houses. We want to go to 34. It's right here. Yep. Do you see, ladies and gentlemen, that DX is going to contain 5E6 after the move? Do you see that? Oh, I can't. Well, it kind of looked 0. That's true. Might look like an E. No, I'm right. I know. The move ECX, ES colon BX. Okay. The base address was 80300038. Okay. So we're after the beginning byte is at 3C. Do you see that? So it starts here. Do you see that? Everyone? Aaron, go. Do you have a question? Okay. Gotcha. Yeah, I know. So sorry. So the least significant byte of ECX is going to be 45. How many bytes are moved? 32. 32 bits, so 4 bytes. That entire row gets copied into ECX. Okay. That's how segmentation works. Well, okay. I'm glad you mentioned that. What would happen? Noah spilled the beans up. Um, if what would happen if we had this? Suppose SI equaled 0010 hex, 10 hex, 310. What would this generate? Everything would be the same, right? Except for instead of adding 4 to the base address, it would try to add 10 to it. What's the limit? 7. It would throw it's beyond the limit. Well, it can't, it's beyond the segment. Does that make sense? Go. Right, but it's beyond the limit. The offset is bigger than the limit. That's one of the first checks the processor does. You get a segmentation fault, also known as a no general protection fault. Is caused by one of two things. The offset is greater than the limit. Does that make sense? You're trying to access something beyond the limit of the segment. Okay. Or you don't have access rights. And that's by that access field that long arrest. Okay. Does that make sense? And as Noah mentioned, it's also called a segmentation. And it's caused by one of those two conditions. Okay. Usually they end up with blue screens, although maybe the IDs are a little bit better. You guys are totally. You haven't lived until you lost 6 hours to a GP. I remember that. You have. You have. Yeah. So, yeah, you get a, if you get a GPF, maybe DOSs are probably a little bit better, but back in the night, 98, 95 days, the operating systems were, well, they were buggier than Ohio in the month of June. And you get a GPF and you lost everything. And you're like, who is general protection and why is he at fault? Anyway, so any questions on segmentation, guys? So now we can go through paging. Talk to me. Okay. Can I reboot the board? Going once, twice. Okay, we can do this. Maybe I can zoom. Can I zoom out? Um, is it still legible? At least on Discord? So go to like maybe 80. How do you, oh, I have to do this. How's that? 85? How's that? Okay. So, and we do this because the projectors aren't right. Okay. Now, we found the linear addresses, ladies and gentlemen, did we not? We can figure, I think that was a three, I don't remember what, it's three, yeah, that was C. No, because we added, it was 3/8. These are linear addresses. Now, again, we're being lied to. The bytes don't reside at the linear address. The way, if paging exists, okay, and paging always, okay, paging takes the linear address and it breaks it up into fields called page directory entry, page table entry, and an offset. And I'm going to explain all of this right now. Okay. Start paging in x86 processors that support it, which is like 386 and up. So paging and segmentation have been supported definitely since the 83, 86, 1990 or 1985, somewhere in there. They were 100% supported. Software didn't take advantage of it, not until Windows NT, but the hardware supported it in 85. And we still use segmentation and paging today, whether it's Windows, Linux, Ubuntu, whatever. One or both of those mechanisms is used, okay? So, did Intel get it right? Guys, they're still being used. They nailed it, okay? Now it's been tweaked, of course, right? The paging in the x86 processors is the defaults are default page frame is 4 kilobytes. Okay. When you think of pages, what you need to do is think of a frame, like a picture frame. Well, what's a picture? It's a container, is it not? The data inside is a picture. Okay. All right. All of the frames are 4K. Why? Because Intel said so. All right. You gotta figure it out. You gotta set something, right? Okay. And I'm sure they did lots and lots of studies and all that. It was, guys, it was 4K back in 1985, is 4K today. Pretty sure that's a fairly reasonable size because they would have changed it if. Then Nick, if you're trying to hang a poster instead of a little 4 kilobyte, little thing that I don't. Rebecca made a bunch of Valentines, so those would fit in a regular frame, right? 4K. Are your Valentines 4K? So Nick's a big guy. He wants big posters, right? Well, then, do you think Intel had NIC in mind? Yes, they did. Yes, they did. There's a bit that sets the page size to 4 meg, I think. Okay. There's a price for doing that. What is it? Not really, no. In fact, it's faster. Not resources, no. How many kilobyte page frames exist in a 4 gig memory space? No, 4 gig over 4K is 4 meg. No, 1 meg. 1 meg. Go the other way. What if they're 4 meg? You only have 1,000 1K. You have uh, the number of page frames is reduced by a factor. You nailed it. Nailed it. Okay. Think about it, guys. We got memory land, right? Memory land's not infinite, right? If we put a bunch of gigundo blocks in memory land, doesn't it stand to reason that we're going to have fewer of them? Fewer blocks? They're bigger, but they're fewer. Okay. The default is 4K. What does that tell? It works for most users. Okay. Now, if you're doing some incredibly heavy duty calculations with gigantic arrays and things like that, you need the 4 meg page set. Joe Schmo running, checking stuff on eBay and Amazon and Facebook. God, 3 things that are a total, well, maybe not a total. Okay, fine. Facebook, though, isn't that a waste of bandwidth? Thank you. Anyway, okay. So it is. It is. So, guys, since the page frames are 4K, how many bits do we need to specify an offset within the frame? We have to go anywhere from 0 offset all the way up to 4K offset. How many bits? Come on, don't let me down. 2 to the 12. The offset is 12 bits. Okay. So here's what's going on, guys. Here's our linear address. Okay. We have a directory field, 10 bit. We have a table field, 10 bit. We have an offset field. How big? How big? $12 bit, yes, no? How many bits do we get? It better add up to 32 or we'd have something wrong, right? 32 bit. That'd be okay. So what we do, guys, is we take the linear address and we break it up into that format. You ready? We have the technology. We can do this. How do you do it, guys? First 10 bits. Guys, there's easy hex nibbles, right? What was this? What was this? Was it an F? I think it was an F. 80F0F. Yeah, it was definitely an F. 1111 0000 1111 Do we need to go any further? Do you see that the offset is 934 hex? Least significant 12 bits. Well, that's the least significant 3 nibbles. So, nailed it. Was that X? Did I put that in the right spot? Yes, I did. What's the other offset? Frame offset. Nailed it. Now the fun starts. Okay. The first 5 nibbles are here. The first 10 bits of those 5 nibbles is right there, is it not? Here to here. That's 10 bits. Trust me, it is. What I love. Don't answer that. What's page? What's page directory entry? I get a 203. Is that right? Just so 203 goes in the page directory entry. Yes, no? Because it's entry 203 in the page directory. What do we have for the other one? Oh, I didn't do it. 1000000001100. Okay. Split it right here, guys. I get a 200. Yes, no? And here I get an entry. This is an F. This is a 0. This is a 3. One, two, three, four. 1, 2, 3, 4. That's a 0, 0, 1. So 1, 0. Okay, that's fine. Don't worry, no. This is a 300, is it not? Page table entry for the second access. Now I have to explain to you how the directories and tables. What's the matter, Justin? You can't read my writing, really? I'm hurt. I'm hurt. Can you see a 3-0 off? Now, I've been struggling. I've been thinking about this all day in between muffins and things like that. And pizza. The pizza was kind of tasty. So think of a directory as a file cab. Okay. I'm trying to think, making sure I get it right. So in a file cabinet, you have multiple drawers, right? Well, how do you know which drawer to go? Well, that's the page directory and which drawer in the file. That makes sense, kind of. Okay. So once you're in that drawer, you got a whole mess of stuff in there, don't you? Well, that's where the page table comes. Okay. The page table references which file in that cabinet, in that drawer, in that cabinet you're going to go to. it's very long. It's a very long drawer because there's four, or I'm sorry, there's 1,000 files. Go. Something like that. The Dewey Decimal System has been likened to paging quite a bit. There have been quite a few analogies drawn, and I'd have to study up on it. But I would not be one bit surprised if really good analogy. So once you're in once you know, because the page table entry tells you which file to go inside the drawer in the file cabinet. Okay. So now we're in the right file, right? We're in the right page. Well, we have to figure out which item inside that file. Does that make sense? It's the best analogy I can. So now a couple things you need to know. Couple things you need to know. For one thing, where is the page directory? Well, that is specified in a special register called CR. Okay. So the address of the page directory, the base address, is CR3. Ooh, I just thought of a good way to CR3 ANDed with 0x 0 at we got to clear out the least significant 12 bits, I think. 12 bits. ANDed with F, 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 0, 0, 0. We're clearing out the least significant 12 bits, guys. Okay? That's the base address of the page directory. Okay, we're going to find out that we don't need a base address of the page. Find that. We don't need it. That didn't come out right. We don't need a special register. So that's the base address of the page directory entry. The actual address of the page directory entry the drawer, okay? The address of the drawer equals the page directory base address plus the page directory entry times 4. There's a reason for it. We're not just pulling constants out of the air. There's a reason. What's that? First off, does that make sense? I really hope it does, because it's the same format as everything we've done. So you have a base address, you have an offset. You have the offset to the base address that gets you where you need to go, address. Okay. Why the 4? Well, each entry is 4 bytes. Okay. Each page directory entry is 4 bytes big. Okay. So if you have entry number 0, that's going to occupy offset 0 to, right? 4 bytes. And then go. There's 1,000 entries in a page. Well, yeah, kind of. But in the page directory, there's 1,000 entries. Each entry is 4 bytes. So the page directory is 4 kilobytes big. Do you see that? 4 kilobytes big. But it's only got 1,000 entries because each one's okay. So if you need to know the base address, which we do, we need to know that. We take the base address and multiply the page directory entry, which is the page directory number. It's a number times 4. Okay. So what do we have here? We have 203. Yes, no? Can I clobber this? What do we need to do? Right here? Okay. So we have a page directory address of 203. Yes, no? Hex. Multiply that by 4. Easiest way. Multiply this by 4. Just do your hex multiplication. This one's easy. What's 3 times 4? Hex. C. What's 4 times 0?
0.
Okay. What's 4 times 2?
8.
I can do that in my head. This is the offset. So add, where does the page directory start?
It's the first 5. So 0291800.
0291800. 80C.
Off. Charging
You know what?
battery.
I can do that in my head. Do you really think it's in the copy, bam, you got your 32 bits. Okay? Does that make sense, guys? Yeah.
Yep.
What about the other one? Can we do the other one in our head? What's 200 times 4? Access Y. The page directory entry is at 0x0291800, right?
Mm-hmm.
Guys, do you see that?
Yes.
Yeah. There's another 8.
Or you forgot an 8. It should be 29188.
Does that make sense? It's a lot of information, I know.
There's still more.
But is it making sense?
Yes.
Yes.
So we answered these, right?
Yep.
Right,
Yes.
guys?
Yes.
Can I scroll up? This is the excerpt from the page directory. Okay? All right. If the stars and planets aligned and I didn't screw anything up, we're going to see what the actual entries are.
Right there.
That work?
Yep.
Okay. Can I clobber this stuff
Yeah.
in the
Yep.
middle? So we know the address for the page directory entry for each access. this one was, yes, no?
Yes.
Yes.
Okay, where's this at? 029188 0C, yes, no?
Yes.
This bad boy? Yep. This is the base address of access axis page table. Okay. Tells us where to file it. Or it doesn't tell us which file, it tells us where that file is in the drawer. How about this one?
3 down from.
Isn't that this bad boy?
So this is going to be 03H4C642.
Yep. Now, there is a format. Okay, that's fine. Cool. There's a format that I can't remember. We're going to clobber again the least significant 3 nibbles. Okay? To find the actual base address. Okay? There's a template you have to apply. Okay? So I lied to you. This isn't the base address. We gotta zero. We gotta zero out the least significant 3 nibbles. That'll be the base address. Okay? Does that make sense? So what we're gonna do, the page directory entry, we can. This was X, so this is a 02 A4 6F EF. And this one was a 02 A4 C642. Thank you. C6, not 6C. The base address, guys, it's the same thing. You just clobber the least significant 3 nibbles. Okay? So the base address of the page table is 02A46000. For the first one, it's 02A4C000. Man, this makes me seasick. The projectors are bouncing. Does that make sense, guys? So how do we find the actual address of the page table entry? How do we find it? Well, didn't we have this up here?
So just add that on, multiply it by 4.
You nailed it. If the page directory entries are double word, 4 byte, what do you think the page table entries are? 4 byte, because everything's 32-bit when it comes to addressing. You guys online, thank you. Seriously. So I don't remember what those entries were, guys. What were the pages? 30F. 30F. Okay. And that was for X. Yes, no? Did I do that right? Okay. Multiply this by 4, right? That means we convert to binary. We could do it the long way too. I'm going to convert it to binary and slap 2 zeros on the end. Okay, guys? Yes, no? That's my original value. Slap 2 zeros. I have a C here. I have a 3 here. I have a C here, right? Is that right? Yes, no? Did I do that right? My bad. No, that's my fault. Is that a little better? How about the, so this is the offset, okay? So we can actually fill this out now, can we not? What do I write? You tell me what to write this time, guys. What do I write? What do I write for the next one, guys? What was the page? Was it 300? Exactly. 300. So I copy this, right? For Y, I copy this value here, 0 to A for C. What? Shout it up? Yeah. Okay. That's the address of the page table. And okay. This is the page directory. You ready to go to the page tables? Are we ready to go to the page tables? You have to go? Oh, yes. Yes. Okay, you guys ready? We're good. Yeah, I know. I know. Things never work out the way you think they. So what are I'm erasing everything, so I need you guys to tell me what to write. And I need to also, we're almost there, guys. What are the page, what are these 02 something? What are right here? This is the values we just, zero. And for Y, it was 02, A4, CC. Okay. What's the page table at those addresses? 02, A4, 6C, 3C. I get this guy right here for X. Is that correct? Where's Y at? Is that here? A4, C2, 9, right? Okay. Ladies and gentlemen, when we found the page directory entry, what did we do? We clobbered the nibbles, hex digits. But I do. Last 12 bits. So we clobber them, right? So the base address for X for the page frame, this is a physical address, guys. Okay? That should send goosebumps up and down your spine. This is the physical address. You feel it, Justin? Oh, yeah. Absolutely. And we clobber the least significant 3 nibbles, right? Find the, right? What about the next one? Same thing, only different, right? A4C000. Those are the page frame base addresses, right? Now, what are the physical addresses that we're dealing with? We take for X, what was the offset? So we take this, right? The base address, and we add 934 hex to it. Did we really add? Go, Justin. No, no, because remember the offset is 12-bit, okay? And it can't be times 4 because what if we only need a byte? We have to be able to specify anything. So we can't multiply it by, that makes sense? That was a great question. So we take this, right? 0, 2, A, 4, 1, and we add 934. It's not really adding, we just plop a 934 after, right? This is for X. Yes, now? What's the physical address for Y? Well, 0, 2, A4C, right? What was the frame offset? Okay. So now that we know the physical addresses, we can go into memory land and figure out where the bytes are, can't we? You bet we can. Notice I was finally smart and I didn't erase the information we need. I deserve a gold star for that. So where's the physical address of X? 0, 2. Well, everything's 0, 2. Here's the memory address. Okay. 0, 2, A4. Everything's A4. 1934, right? Right in the middle of the Depression. Yes, no? This is X. I don't remember. Was X 2 bytes, 1 byte? 4? X was 2 bytes moved, right? So 1245, right? Is that what we had before? Should be. Right? So right? Yeah. I copied the linear address contents to this table, so it, no, I forced it to match. So I'm giving away all my secrets. Where's the other physical address, guys? 02A4C, right? That's over here. Yes, no? 3C? There? So was it ECX? 93 5E? And that's a D, not a 0. So, ladies and gentlemen, we have traced logical addresses, linear addresses, all the way to physical. This is how it works, okay? And it can be summarized by this. Are there any questions on the work? I got 100. Well, we got 100. Okay. Not in embedded systems, no. Oh my God. So, are there any questions? Any questions online? What we've discussed, guys, can be summarized. This is the page directory entry format. Do you see how we clobber the least significant 12 bits? Because they mean other things. One of them is no, it's on the page table, I think. No, it's right here, the D bit. Yep. It's called the dirty bit. I have no idea why. A page is dirty if it's been written to. Okay? And if it's been written to, guys, think about it. That page probably came from the hard drive. Even if it didn't, it was created by the program, by the application when it started. Well, it started off at a certain value, okay, and then it got modified. Okay? You have to know if it's been modified because if nothing else, we haven't talked about this, but cache is a copy of RAM. Why do we have cache? Faster. Auxiliary. Okay. So if the page in cache differs from the page in RAM, that could be a problem if that discrepancy isn't taken care of at some point. And the operating system and the memory management system takes care of all of that. But for speed purposes, do you see that knowing whether the page has been changed or not is crucial? You're not going to go through the trouble of, writing pages back to RAM and then the hard drive if they haven't been changed. Why would you? Okay, so the OS keeps track of the dirty. Go Nick. Okay, I think. Don't quote me on this, please. I think, yeah, I think Windows uses a write through strat. What does that mean? Well, I'll explain what the strategies mean. Therefore, I'm tiny bit. A write back, a write back strategy means that if if a page is written to, it's just written to cat, not to RAM, not to the hard drive. It's only written to main memory RAM and or the hard drive only when that page has to be eliminated from memory to make room for others. That's called write back. Okay. It's only written when the page is replaced. Okay. Write through means that if a page has to be modified, its copy and cache is modified first, of course, but then the memory management system takes that and writes that change all the way through, theoretically, to the hard drive. Shout it out. Write through is yes. Full replacement, but only when the page has to be eliminated from memory. Okay? Which is faster overall? Right back. Right back. Yep. Which would, watch my fingers, which would theoretically be safer. Right through. I think Windows uses right through. Don't quote me on that. But I think it uses right through. Okay. That's the page directory entry, page table entry. Very similar, is it not? Nick, you were talking about your poster size. Size bit. We did a mental exercise, one of the embedded systems classes in years past, and we tried to figure out a way to make this where the OS could make the size changeable on the fly. We couldn't come up with a way. Do you see why? if the OS has a bunch of pages in RAM based on 4K, oh, we're going to go to 4 meg now. Do you see everything would get totally jacked up, right? I mean, you'd have to rearrange everything. Yeah, yeah. And it might not even be possible. Might not be possible. Everything we've discussed tonight, here's this. This is with 4 megabyte paging, okay? With 4 megabyte paging, we don't go through a table entry. Okay? We don't need to. They're 4 megabyte pages. If nothing else, the page frame offset it's 4 meg. The page frame offset has to be 22-bit. Yeah, but again, it's 4K and it's I don't know of anyone who uses 4 meg. I'm sure they're out there, but I don't know where. Now, a couple of things. Do you see that paging and segmentation, for that matter, you should be thinking, wait a minute, this is a lot of memory access just to get contents written or read from memory, right? Think about it. Even after segmentation, there's a memory access to get the page directory entry. That's a memory access. There's a memory access to get the page table in. And then finally, we can go and get the actual data, right? Right? So just in paging alone, there's an extra 2 memory act, period. Well, what they do is inside the processor are a bunch of memory locations inside the processor, so they're instantaneously available. They're called translation look-aside buffers. They are copies of recently used page directory and page. Okay, so if the page table address calls for something that's been used, and we know that it's highly likely because of locality, do we not? Right? It just uses a translation look. Okay. Absolutely. Absolutely. Yeah. Yep. And the actual location of memory land of that paragraph or whatever it is in your Word document, that would be saved in the translation. So it wouldn't have to go and grab that information from memory. Yeah, kind of. Yeah, absolutely. This is what it looks like, guys. And I really think it's been suggested, and nobody's ever done it. This should be on the back of ACM t-shirts. Wouldn't it? Sure would raise, you'd probably get some eyebrows, but definitely some interesting questions at the checkout line at the grocery. You're not? Like, what the hell is that? Well, no, just call it paging and segmentation. That it's the total truth. Do you see how it works? The logical address at your program goes through segmentation to generate a linear address. Linear address goes through page directory entry followed by page table entry to get the physical frame, and then the offset is added to that to get the actual data that you're in. And if you don't think that's cool, then you're probably in the wrong. Sorry. Actually, no apology. I'm not. Go. Your assumption is correct. Okay, the tables have the base address. These form offsets in relation to the base, like you just said. Absolutely, you nailed it. Do you see that with segmentation and paging, if you wanted to go straight, if you wanted to eliminate segmentation, yeah. Well, it wouldn't be complex to the user. Everything would be 4K, right? So that kind of goes back to the, do you want variable segments? Because pages are constant. Yeah, yeah, yes. But paging is necessary because that's the way the hardware is designed. That is physically the way the hardware is designed. 4K page, period. Oh, absolutely, right? Right? Logical to linear. This is all software. This is all, watch my, this, it's all fictitious, right? A logical address isn't really an address. It kind of is, I guess. Yeah, you could think of it that way, probably. But once you get to the linear address, now we're talking real. Yeah, kind of, I guess. Yeah. So, Nick, you're president. Make it happen. Any questions? Um, yeah, you C++ites like to compare everything to pointers. C2. Yeah. It's not called a pointer, it's called it's called an offset. It is. It is, guys. You could think of this as pointers into an area of memory. Which area of memory? Well, what's the base address? That specifies everything, does it not? Yes, if you know C, you can liken everything to pointers. Absolutely. In fact, in assembly language, computer architecture, we refer to an offset register or an index register as pointing to a certain place in memory. Okay? Good job, guys. Very good job. Excellent job. Any questions online? Brendan, you still there?
I'm still here.
Any questions, Brendan? I hope you enjoyed that.
I did. Thank you.
You're welcome. You're welcome. Good to hear from you. All right, I'm going to sign out and go home. All right. Thank you for coming. Thank you for coming. Thank you for listening. You're welcome.